Good morning. So today's lecture will continue on the chapter 0 notes. So we already discussed about the digital systems. So for digital systems, it can be like the computers, it can be the circuit boards, we call it PCB, sometimes printed circuit boards or any circuit boards, the chips, like different chips, different microprocessors, the logic gates, and or all of these gates, and the transistors as well. So all of these are parts of digital systems, and then in order to use them, we need to something we call it quantize or digitalize the inputs. So in order to process this, we need to convert the analog to digital. So you through the analog to digital converter, then make the analysis after that, make digital to analog, and so on. For the hardware system, sometimes, since it's based on 0 or 1, sometimes switches on will be 1, switches off will be 0. So there are several definitions. Some definitions will define the 1 as 5 volts, the 0 at -5. This is, for example, some discrete values in 0 and 1, sometimes between 0 and 5. So 0 will give 0 volts, 1 will give 5 volts. So depending on the chip or depending on the device itself. So whenever there is a -5, this means it is 0. When there is a 5, this means 1, and so on. The digital circuits analysis. So basically, our target in this course, because it's called digital logic circuits, there should be inputs, outputs. I have some inputs, and I need to have a desired outputs. So what should I do to get this desired outputs? I need to make an own design. I need to make a design like this. Here we have inputs, we have desired outputs. How can I make my design? Which is called digital logic or digital circuit. So I need to build a circuits that can satisfy my targets. It looks like hardware programming, as I mentioned earlier. So we need to design something to satisfy the requirements. For example, I need to design a traffic lights. I have the inputs, which are, for example, like I can have timers, I can have coordination between the traffic lights, I can have also sensors to detect how is the traffic, is it heavy or not, or if there is any cars are coming or not. So it depends on the application. I have some inputs, and the outputs is to run this system. I need to have a desired output. So I need to make sure, for example, if this street is has heavy traffic, then the light or green light will be on for more time than others. If there is no other cars, then stop and make it red. Let's go green for the other cars, and so on. So you need to have desired, and you have your own system. On the same way that when you are building a thermometers or a thermostats for your AC or air conditioning. So in air conditioning, you have the actual temperature, and you have your target to reach the desired temperature. So your actual temperature, whatever it is, and the desired temperature to be 70. And when you are, or also when you are driving a car and like cruise control 70 miles per hour, so something like that. This cannot be achieved only in digital logic circuit. It can be achieved in different type of controllers, as I mentioned earlier. But again, in this course, we will go into hardware programming, which is how to build a circuit that can satisfy this without going to the software and building a software, so just building hardware programming. That's why I think this course is in electrical engineering, not in computer engineering or in software engineering departments, because most likely whenever anything related to the hardware, this will be in electrical and computer engineering. Okay, so the inputs and the outputs can be either discrete or it can be analog. So whenever, since we are building the digital circuit or digital system, if it is analog, we need to convert this to discrete, which is why we call it digitalize or quantize this. After that, we need to convert this to binaries, 0 and 1. How did we do this? Like the same way that I mentioned earlier, last lecture. So we can make quantize, for example, this. Or first, I have an audio. It will be stored. Convert the microphone, will convert this audio from audio to electrical signal. This, for example, a sample of the electrical signal. Then it will be quantized as shown here. So it will be stored as numbers instead of this graph. And these numbers will be stored in binary so the computer can understand it. Then it will be stored as zeros and ones as shown here. Then the digital circuit will be after this step. We will not worry about how to make conversion between analog to digital or how to discretize. We will assume everything has been done before. So our targets, we have binary inputs. We need to get, or we have a specific inputs, we need to get a specific outputs. That's what we will study early in this course. The battery state. This, yes. So in this course first, we will keep in mind, look at how to make the design in simple way. Then after that, we will go in more complicated step by step. But before going to the designs, we need to learn the basics or the alphabets of the digital logic circuits, which is the definitions of the binaries, the definitions of the systems, what are the components of the logic circuits, how can we use these components. After that, we can build our own design. So we should expect to see in the first 2 weeks or 3 weeks, some methods or some definitions how to use this stuff or define what are these stuff. Then after that, we will apply them later in the design. So it will be more fun later when we try to apply this in real life. Okay, so as we know, the analog is continuous signal, while the discrete, there are sample. When the sample rate is high, it will be more accurate depending on the processor, depending on the manufacturer of the device, depending on the physical device that I have. So hardware systems, as we know, the binary system, it can be either zeros or ones. Binary systems, it can be 0 or 1. For example, if it is on, switch is on 5 volts, if it is off 0 volts, or sometimes -5, depending on, again, on the manufacturer or depending on the system. But most likely, we will assume in this course on 5 volts, off 0 volts. You don't need to worry a lot about the 5 volts or the 0 volts. We need to worry about later in the design, which is 0 or 1. So whenever the transistor is on or the transistor is off, because the transistor will act as a switch, as I mentioned earlier. So if the switch is on, there's current flowing, then it will be on, light will be on, current will be on. If switch is off, there will be no currents, light will be off. So it will be 0 volts. So what's the advantages of using the binary system? Why did we switch to this? Because most likely the mathematical expression for it, it will be much easier for us. And dealing with zeros and ones, there will be no fuzzy, nothing in the middle. It's either white or black, so no gray area, or 0 or 1. So, and we can use this in the programming. For example, this simple program. If the garage door is open and the car is running, then the car can be backed out of the garage. So it can be like on, off. So it can be the door either open or closed. It cannot be half open or half closed. And the same way, like the car can be on and off. So we can use this logic. That's why it's called logic, because it can be yes or no. So if both door must be open and the car running before I can back out. These two conditions must meet. So my inputs are the garage door and the car. The outputs is the car to leave or to go back out of the garage. How can I satisfy this? Read the status of the car, read the status of the garage door. If both are on, then let it go. If not, don't move. Okay? So we can put this small command like using and or gates, as we will see this later. So this condition must be true to go to the outputs. So for example, the design will be, okay, I have this input, I have output. How can I design the circuits that can allow this condition to meet? So we will discuss this later. We're still in the introduction, so we will not go to the design here yet. Binaries, or a group of binary, some definitions. We know, again, the binary, it can be 0 or 1. This is the logic, 0 or 1, which is the base here. Base is 2. Whenever there is a base, so we have only 2 digits, which either be 0 or 1. That's what does base 2 mean. When there is base 10, 0 to 9, and so on. So when we, let's assume that I need to count. So we can say 0, 1, then what else? 10, 11, then 100, 101, 110, 111. That's how we count. Because we have only 0 and 1. There is no 2, no 3. That's if we need, to count up for the binary. Then we have only 2 significant digits, 0 and 1. Again, on and off. That's it. That's all of what we have. So a bit, it can be a single binary digits. It can be only single binary digits, which is only 1. When there is a group of 4 bits, we call it nipple. When there is a byte, 8 bits. A word, it's depending on the microprocessor. If this word is combination of 8 bits, 16 bits, 32, 64 bits. Let's recall the old computers. The old computers, there was 8 bits. I still remember this in the old days. There was 8 bits computer. Then after that, they say, oh, there's a 16-bit, which is much faster computer. Then we switch to 16 bits. Then later they say, okay, 32. Then 32 is much greater than that. And nowadays we see a combination, 32 and 64. Both of them are functioning well, but the most common now, or the trend go through toward to 64 bits. So it's depending on the microprocessor. So if the microprocessor on your computer or software is based on 64 bits, so each word or each word, we call it here word, will be stored as 64 bits. Or we can say each letter even. So but here we call it word because we don't mean by the word the whole word, word of the, for example, a word hello. For example, let me say a word hello. This does not mean the whole word will be stored as 64 bits. Each letter will be 64, this will be 64, and so on. But we will call it a word because it will be stored into the microprocessor as this way. Okay? Then there is also something we call least significant bits, which is on the right, there is the most significant bits on the left. What do you mean by that? It's normal, like you see here the counting, it's normal to, if I put the missing are zeros, the missing bits are zeros, it's normal to say that here is the lowest number, here is the largest number, right? When we count this, we will say here is the largest digit, here is the largest digit, here is the smallest. Right? Then this thing, since it's the smallest weight, we call it least significant bits. This is the largest, most significant bits. Okay? Because, of course, 111 is, or let me say 100 is larger than 1, even in binary, right? So 100, the weight of it is larger than that. It's in the hundredths decimal points. But ones, it's in the beginning. So let me assume we have 8 bits, or in other words, this 8 bits is 1 byte or 2 nipple. And I'm going to assume it like this. So here is 1 0 0 1 1 0 1 1. So we can say that since it's all 8s, so this is 1 byte. Or this is 1 nipple. This is 1 nipple. Or also we can say This is the most significant bit because the largest weight of the digits. This is the lowest significant bit. Okay? Clear? You should memorize these definitions. This is very important. And since it's 1 byte, I'm assuming again, if I assume 8's processor, then we can say this is a word. So this is 1 word. If we have 16 processor, then it has 2 bytes. If we have 32 processor, it has 4 bytes. If we have 64, 8 bytes. Okay? You should be aware of this. It's just multiple of 8s. Now for the representations. So again, I mentioned the binary representation. It can be 0 or 1 because it's binary. Why we choose this? Why we choose 0 and 1? Because it's again based in logic. And logic, it can be true or false, or light is on, light is off. Transistor is on, transistor is off. The inventing of the transistor, creating this revolution, then we can make it. In the past, it was vacuum tube. Now we no longer need it, so we can make it as transistor. So it can be 0 or 1. Then that's it. So there are other groups of symbols that we can use in our real life, like the English letters, 26 from A to Z. We can use A, B, C, D, Z. Why we didn't use this? Because it's maybe more complicated. And how can we apply it in real life? Like, is there a switch that has 26 status? You can create like this, but it will be too complicated. Then also, like the symbol for groups like 50 states of United States. Okay, this is just symbols. 10 decimal points, 10 decimal digits, which is the digits that we know from 0 to 9. Even the number 10 is a combination of 2 digits. So the 10 is a combination of 2, and so on. The 100 is a combination. Then the basics are from 0 to 9. So since it's base 10, then we have 10 symbols to represent this. So digital systems manipulates 1 or 0, which is on and off. Then when we make a mapping of these symbols in binary, which is known as code, creating a code as well. So the mapping, of course, must be unique to give you to give, like, there's a unique 0 only for off, 1 for on. We cannot make a combination, like sometimes use 0 for on. So we need to be like consistent. We need to be unique with this. Okay, so numbers are based on digits. So when we have a numbers, we need to make discretized, because in digital systems only accept 0 and 1. So how can we make these numbers to be zeros and ones? Convert this to be from numbers, for example, using ASCII code or using some other representation to convert it to zeros and ones. When we have letters, again, we can use, like as I mentioned earlier, ASCII code, and there's universal code, different type of codes that can be applied. Then all of this will be stored as zeros and ones. Pictures, pixels. Pictures, when you zoom for the pictures, depending on how's the accuracy, so you will realize the pictures is a combination of pixels, and each pixel has its own color. So the full pixel will be a unique color, and that unique color has its own code. Then this code will be as a number, then this number will be converted back to binary. So that's how everything will be stored as digital. That's why we call it digital era or digital systems. Now, where everything is being digitalized, so everything will be stored, even my voice, your picture, the video, everything will be stored as numbers, as digitals. And at the end, it will be as zeros and ones, which is as a transistor, which is the transistor will, we can record everything and store this using zeros and ones. So how our numbers will be represented in digital systems? That's Chapter 1 will be how can we represent these numbers into digital systems. So how the computer performs basic arithmetic operation, this will be different later in this course. So this is the end of Chapter 0. Any questions about it? Okay. Now we will go to chapter 1, which is the numbers in real life. Now, in real life, or like based on our reference, we are using the numbers from 0 to 10. That's the common that we used to do. We used to have it even from pre-K until now. So why we are using the base of 10? We already agreed that the numbers base of 10 from 0 to 9, then after 9 it will be 10, go to the other digit and so on. Why we didn't say from 0 to 8, or why we didn't say use binary in our life? No one knows, maybe because our fingers are 10, but that's what we are using in our life. Then we are getting used to it, and we are using in real life. Then we cannot, say, okay, let's use something else, because this is in our daily life, in our financial and everything, in our calculation. We cannot do that. But this does not mean I cannot use others. I can use others, other format like the binary representation, but I need to convert between these two. I need to convert between binary to digital, or convert between other systems. So, in real life, we are using the base of 10. So let me talk a little bit about base of 10, then we will see the other bases. So, in base of 10, we have 10 distinguished, or 10 unique symbols to produce 10. So why we create like 0, 1, 2, 3, 4, 5, 6? This is indicates of what? Why these symbols has been created like this. Anybody knows why? Why we made the symbol 0 like this? Yes.
Is it because you can make any numbers if there's 10 digits?
Yeah, but why they choose this shape? Why they choose the 0 as O, the 1 like this? Okay, the answer why I'm gonna see. I'll show you this here on the PC. Actually, as you know, these numbers are basically called Arabic numbers. So these numbers, when you look at 0, which is O, there is no angles, right? Then 0 angles. That's why the symbol of 0. Look at 1. There is only one angle, right? Then this is 1. Look at 2, 2 angles. 3, 3 angles. 4, 4 angles, and so on. 5, 6, 7, 8, and 9. Then these numbers, or this shape of these symbols, I'm not sure if it's Al-Khwarizmi. I'm not sure who's created. I think Al-Khwarizmi, which is the word algorithm comes from Al-Khwarizmi. I'm not exactly sure the spelling. I know it in Arabic, I don't know exactly in English. But these numbers has been defined because of the angles. Then we use these numbers in real life. Then our brain understands this without looking at the angles right now. But that's the origin of these numbers, based on the angles. Then these symbols has been created for us. Let's go back to the notes here. So we are using these unique digits to represent the numbers originally from the angles. Then these numbers can be represented as a sequence. So the least significant bits on the right, the most significant bits on the left. Then the value of the number based on the positions. That's something we call it positional notation. So the position or the location of the number matters. We cannot say, okay, I'm going to put here 1, 2, 3. We cannot say 1 alone, 2 alone, 3 alone, unless we put comma, you put something. This will be different. But if there are here, then we can realize that this one is actually 1 times 10 power 10, 2. This 2 is actually 2 times 10 power 1. This 3 is actually 3 times 10 power 0, right? This thing, we call it the positional notation. This means if we swap 2 and 1, this will change the whole value. They are not equal to each other. This matters. Then the position matters. Okay? And everyone is aware of this, but here I'm trying to show you in the base of 10, then when we can go to the other bases, you can have a clear image how to use this. So if we learn how to use this, or recall how to use this in binary, then we can, or in decimal, we can be aware how to use this in binary and use it in other things. So we have general equation, which is the sum. This number can be represented as the sum of each bit times 10 power the location of it. Then there might be a decimal point, right? If there's a decimal point, after the decimal point will be a negative 10 power negative something. Like what? Let me say 1.23. So this is 1, the location of it is 0, so 1 times 10 power 0. Then 2, it will be 2 times 10 power negative 1. 3 times 10 power negative 2. When you go far away from the decimal point, you will add the negative power. When you go on the left of the decimal point, you will add positive. So what matters for us, we're determining where is the location of the 0, is the one on the left right after the decimal point. This will be the 0, the power 0. Otherwise, you will go up or you will go positive. After the decimal point, you will go negative. Again, we are all aware of this, but here just to recall, because we will use it later in different systems. Now, how do we represent this number? Let's assume this number as base 10. Sometimes you will see a brackets and here sub 10. This means this number, sometimes if you're in digital logic circuits, this number is written on base of 10. Some bases that we will learn later, it will be in base of 16, which is we call it hexadecimal, or in base of 8, which is octal, or base of 2, which is binary. So sometimes we put this so you can understand this is in base of 10. Most likely, if there is no base associated with it, then the default is decimal. So here, the base of 10, how can we write this number in a base of 10? So it's 1, 2, 3, 4.56. Now, the location of this. This is the decimal point, so the location is 0. This is the location of 1, location 2, location 3. This is location negative 1, location negative 2, right? Do you agree? Yes. So how can we represent this as decimal notation or positional notation? It will be starts from the left. 1 times 10 power 3 plus 2 times 10 power 2 plus 1 times 10 power 1 plus 0 times 10 power, I'm sorry. This is 3, this is 4, I'm sorry. 1, 2, 3, 4. Plus 3 times 10 power 1 plus 4 times 10 power 0 plus 5 times 10 power negative 1 plus 6 times 10 power negative 2. Okay? Do you agree with me? Now, when you calculate this, you will get the same number after substituting this. 1, 2, 3, 4.56. Okay? Now, when we see any leading zeros here, it shouldn't cause a problem, right? Why? Even if you put 0 here, so the weight is 4, you will say that 0 times 10 power 4. 0 times anything, it will be 0, right? If there is any leading 0 or lagging 0 in the lifts, do you think this will matter? This is negative 3. So plus 0 times 10 power negative 3, it will be 0, right? So zeros in the lefts will not matter, or zeros in the right after the decimal point will not matter. What is matter for us when there is, for example, 1, 2, 3, 4, if I add zeros here, this will change the whole position, right? But if I make 1, 2, 3, and make it like this will not change anything. How about if there's a decimal point, and I said I add zeros here, 1, 2, 3, this will change, right? But if I say here, 1, 2, 3, and add leading zeros, this will not change. This is normal. But here, review again, because we will apply this for different numbers. How about if we have different systems than that we used to have? Now, the base here, 10. How about if I have different base? Like what? Again, hexadecimal, octal, we will see this later. But let me assume a base, we call it R. So we can create a general formula that can valid for any system. So this here, we call it the number systems. Let's make a base R. Then instead of 10, we will say R. And that base R, basically the numbers, when we say base R, it will be between from 0 until R negative 1. R minus 1. So R, we will call it as radix, which means like the base, but we will call it here radix. So how can we deal with the system with base of R? Let's imagine that I have this number, and 5, let me say, and 3, and 2, and 1, and 0, and negative 1. I'm sorry, let me rewrite this. And 3, and 2, and 1, and 0. Here's decimal points, and negative 1, and negative 2, with base R. How can we evaluate this and convert this to the decimal so we can know what's this number, what it is, this number? So it will be n3 is the position of 3, so it's going to be n3 times r power 3 plus n2 times r power 2 plus n1 times r power 1 plus n0 times r power 0 plus n negative 1 times r power negative 1 plus n2 times r power negative 2. So if we know this formula, we can, or if we can apply this formula, we can apply it to any number that we know or any systems that we know in real life. For example, how about if we have something we call octal system? Octal. In octal systems, it's based on R equals 8, based on 8 digits. So we don't have more than 8 digits. What are these 8 digits in the octal? They are basically 0, 1, 2, 3, 4, 5, 6, 7. Don't go to 8. You will go to R minus 1. 8 minus 1, 7. So we have 7 distinguished digits. 8 distinguished digits, sorry. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8. Then for the octal number, there is the definition of number 9 is no longer exists. The definition of number 8 no longer exists. So when we are with octal, let me say 0 octal plus 1 octal, it will be 2 octal as knowing. When I say 4 octal plus 4 octal, it will be what? 4 plus 4, 8. But in octal, there is no number 8. So the largest number is 7. The next number after 7, 10. So it will be 10. So you see, here is the trick. So you need to be aware of a system. Again, the system can handle, like the counting will be 0, 1, 2, 3, 4, 5, 6, 7, 10, 11, 12, 13, 14, 15, 16, 17, 20. You see? You cannot use number 8 at all. You cannot use number 9 at all. 17, after 17, 20, 21, up to 27, then 30, 37. After 37, you will go to 40, and so on. You cannot use any digit related to 8 and 9. It's octal. This is how the system octal will be. So in octal, let me assume that, like, what's the value of 10 in octal? Here is 10 octal. I need to calculate it based on this rule, like the radix rule. So here, the radix R, and this is, I can call it N0, this is N1. According to our rule, it will be N1 times R1 plus N0 times R power 0, right? So let's substitute them. N1 is 1. R1, which is the octal here, the base is R, or the radix is R power 1. Plus N0 is 0. plus 8 power 0. Okay? Do you agree with me? Then 8 power 1, 8 times 1, 8 plus 0 plus 8. I'm sorry, 0 times 8 power 0. 8 power 0 is 1. 0 times 1, 0. So the answer will be 8. And this is when we convert this to our system that we know, which is the decimal. Then we will realize that 10 is in octal is actually equals to 8 in decimal. Right? Do you agree with me? Any questions?
Can you say that again? 8 in decimal is what in octal?
We will realize that 10 in octal equals to 8 in decimal.
Okay.
Okay? Now, how about other base, which is called hexadecimal? And this is very common used in programming. Hexadecimal, this is based on 16 bits. R will be 16. Okay. We have 16 symbols. Then this means we will go from 0 to 15. But we need a unique symbol. We cannot use the symbol 15. We can say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now we cannot use 10. 10 will be 2 digits. How can we make 10 equivalent to hexadecimal? When I show you here the photo that creates 9 angles, so we will say if we need to make a symbols to create 10 angles, this will be much harder. So how can we use the hexadecimal? Yes?
Letters.
Use letters, right. So we can look at the other groups that can, we are now running out of digits. Now let's use letters. We have 26 letters. So let's use letters. Then we can use A, B, C, D, E, and F, right? Do we have F? Yes. So you until F. So F is equivalent to 15, E equivalent to 14, A is equivalent to 10, and so on. Then we are running out of letters, running out of digits or numbers, then we will use letters. Now the letters they have a definition in numbers. So again, the location of it will be very important to determine the value of it. And depending on the position. So we can say that in hexadecimal, we can say 8 in hexadecimal plus 7 in hexadecimal, it will be what? It will equal to, let me say 8 plus 8. 8 plus 8 will be 10 in hexadecimal. Right? So when you see like 8 plus 8, we know it's 16 in our system, in our reference. But with respect to the hexadecimal, it's equivalent to 10. 10 hexadecimal. Okay? How can we analyze like the 10? Let me see. This 10, let's analyze it according to the radix point representation. So the radix point representation, this location is N1, this location is N0, this is the radix. So according to this notation, it's going to be N1 times R power 1 plus N0 times R power 0. N1 here is 1 times R power 1, which is 16 power 1, plus N0 is 0 times 16 power 0. Then it's going to be 16 plus 0, which is going to be 16. This is in decimal. Then we will realize 10 is equal to 16. But depending on the representation. 10 is equal to 16, but 10 hexa equal to 16 decimal. So you need to be aware of all of these quantities. And if we convert this into octal, it will be 20. Is that right? 8. I'm not sure. It will be 16. Yeah, it will be 20, right? Can we prove this? Yes, let's say 2 times 8 power 1 plus 0 times 8 power 0, which is going to be 2 times 8, 16, plus 0, which is going to be 16, which is, yes, correct. Yeah,
How are you doing these conversions in your head?
which is,
Like from hex to octal, how do you just know that? Am I missing something?
do you mean 8 plus 8? I mean, here, I'm just trying to put some examples. Let me give you a demonstration so you can try it. You can try it here now. Now, there is a joke says that December or Christmas equals to Halloween, which is December 25 equals to, or decimal 25 equals to octal 31st, which is, this is a programmable joke. In other words, 25 decimal equals to 31 octal. Can you prove this? You turn. You can try it. I need you to prove that 31 octal equals to 25. Don't play with the 25. Play with the 31. Using the radix representation. Okay, when you try it,